All right, let's get the show on the road. We've got 2 more talks tonight, and next up we have Silvio, who's going to be talking about code forensic analysis.
Yeah. Hello, everyone. Let me know if you don't hear me. Hey, Matt. Needs to stay close to this. Has anyone heard of code forensic analysis here before? Because
TV show CSR.
right? Yeah. Yeah. yeah, definitely. Oops, something's going on here. Again, okay. Yeah, well, it's got something to do with that. I hope you'll find this topic interesting, or at least useful. So I'm going to skip through these slides as quickly as I can. So forgive me if I go fast, because I think the most interesting part of this presentation will be the sort of a demo that I do at the end, where I show some of the things that you can actually do using these techniques. Where does it all start from? Where do I come from? From where most of us come from anyway. There is the cost of software maintenance. And nowadays, I think most of us are familiar with agile methodologies. Probably we use it in some shape or form in our development environment. And in the current, using agile, that means that you normally, because you have an iterative process where you are encouraged to release to production as soon as possible, possibly every iteration, and even after maybe the first or second iteration. That means that you enter, as a software team, you enter development and maintenance mode right away. That is, as soon as you release something to production, you are in maintenance mode because you have to maintain a code that is in production. But what is maintenance? And this is the question that I normally ask, if someone asks me, what do you do for a living? Okay, I'm a software developer, I'm a programmer. And what does that mean? We tend to think, and I used to think, well, my job is to write code, and that's what I do. And no, because I do spend most of my time reading code. And by the time that I understand what to write, well, that's the easy part. And this is, if you reflect on what you're doing every day, I think, most of the time you spend time reading code and try to re-engineer, like reverse engineer, or understand what the code is, even sometimes your own code that maybe you wrote a few weeks or a few months earlier and say, what the hell is it? This is just to introduce the concept of software maintenance has a lot to do with reading and understanding code. And there's I'm going to go quickly through now these symptoms that I believe most of you, especially if you are experienced developers, are familiar with. And these are typical symptoms that affect mostly like large-scale projects, but even small projects tend to become large scale at some point if the project, especially if they are successful, and they tend to grow. And then you start experiencing these and maybe other symptoms, and these are very, typical. And we normally in the industry, we have 2 words to define one of the root causes of this, that is technical debt. And, in this famous diagram by Jim Highsmith, we know that there is a cost that comes with technical debt, a cost that we would like to minimize. What do we do to minimize this cost? Well, we use different techniques. Well, we use refactoring, we use automated testing, we use code reviews, but these techniques are not very scalable as the project scale. And so we also use static code analysis. They've been around for many, many years. I don't know, whoever has used something like Checkstyle in the mid-2000s or something, then, PMD in the Java world, and plenty of other tools. And these tools all have in common, a characteristics of capturing metrics around your code. And we can, the most important metrics are normally duplication, number of lines of code, some sort of complexity, maybe some sort of a dependency. These static analysis tools are useful, and by all means, I've used many of those, but I didn't find them very effective. And one of the big limitations of these tools, most of them at least, is that they give you a snapshot of the current state of your code base. And that snapshot can be misleading. It gives you an idea of where the problem can be, but you don't really know whether those are the real problems. This is, I don't know how many of you maybe use Code Climate. This is what we use in Redbubble. And it's automated in our build process. Every branch, master or non-master, that goes into GitHub is obviously scanned through and analyzed by Code Climate. And I asked around in my company and how many developers actually pay attention to Code Climate, and the results are terrifying because nobody cares. And then I did a quick Google search and I found this. I don't know how reliable, so you know, don't take my word for this, but it's a report in 2013 by Rebel Labs that shows, you know, what kind of, like, how are these tools used? And this distribution of, you know, percentage actually reflects pretty much the same situation that I've experienced over and over again in all the places that I worked. And why are these tools so neglected, or, you know, not really, like, they promise to be so efficient and so effective, but ultimately they are not. And this is where, you know, another quote from Adam Thornhill comes handy, because sometimes, as I said earlier, they highlight problems where problems may not be. And they don't give us enough information to really make well-informed decision when we want to refactor or redesign a part of our system, part of our architecture. And so let's think about a new approach that is not my invention at all. I ended up, like, I was landed a copy of this book about a year ago by a colleague of mine that I started reading, and I found it extremely interesting. And the book is by Adam Thornhill, the person that I mentioned earlier. And there is a word in this in this book that's mentioned forensic. So what is forensic? And, you know, when we hear forensic or read forensic, with crime scene. So if our code is a crime scene and we are the detective, the investigator, right? How do we go about finding the clues that will, you know, lead us to identify the offender or the offenders? And by offender, bear in mind, I don't mean people. We're not looking to, you know, find guilty developers. We're looking to find bad part of the code, like part of the codes that are offending, that are a danger for our system. So, you know, how have we done this? But we've done this in the past. Like, we do this all the time when we feel the pain, when we, you know, work on a part of the system and we feel that it's tangled and it's not written well and we want to refactor this. But then more often than not, we end up finally, like, digging ourselves a bigger hole than where we were in even before. And so we, you know, we retreat back, say, well, I tried to refactor it, but forget it. And why does that happen? Because we can't really assess the benefit that comes from our refactoring based on the effort that we put into it. If we, you know, we can identify a piece of code that needs refactoring, but we can also end up estimating that may take maybe 4 weeks. Is that worth doing it? Does it really bring the benefit? What's the impact in the business? Like, those symptoms that I mentioned earlier, can we affect any of them? We don't really know when we start refactoring the code. And that's why we normally use wishful thinking, gut feel, and, you know, our experience, like, as a detective, to find, you know, the offender. But unfortunately, things are not as good as they are on TV, where, you know, always the good wins and the evil loses. So can we become better detectives and use data that is more, you know, scientific, more forensic, and, you know, and become more scientific in our methodology? And eventually, I mean, that's the dream. Could we become the ultimate detective of all time? That is the one that can prevent a crime before it even happens. I don't know. I have no answer for that. But what do we have? So let's start. So we have version control systems that we have started using quite a while ago. And we don't really exploit all the information that is in there. So there's a lot of information in our version control system. There's technical information, obviously that's the most relevant one, and whatever your code is doing, class names, module names, method names, and other things. There is social information. There's messages that go into GitHub that kind of can tell you something about how developer communicates. And also, obviously, their developer's name or email. There's something that allow you to kind of create a picture of what the social structure of your development team or company is. And there's organizational information, because you can take that information and then knowing how teams are structured, you can start creating, and aggregating data depending on what developer has committed what and who is in what team that developer is, and then start making, further elaboration on that. And all this information can be somehow, in different ways, transformed into metrics. And this is where the killer thing is, that the version control system gives us, it's like a time machine. So we can actually track this stuff in time, and we can actually go back in time. Imagine if a real police detective could go back in time. That would be yeah, my God, I can see who did that, So this is very quickly to summarize. Basically, this is what is at the core of the code forensic technique. And all of these concepts that I really blazing through are very well described in the book that I mentioned earlier. And if you're excited about this topic and interested, I would strongly recommend you to have a read at that book. So what tools do we have today? What tools do, because this is all good and nice and in words, but what can we use? So these are the two tools that I use. One is CodeMath, written by Adam Tony himself, and Code Forensic that I built myself. And how does this work? Very simply, CodeMath is the tool that analyzes Git logs and provides heaps of data by parsing basically not just the Git log, but different repository log files. And Code Forensic is just a tool that takes that data, does some further elaboration, and uses JavaScript to do some rendering and publish some diagrams. And the reason that we need to use, and I thought it's important to use diagrams, is because the data is massive, especially if you have a large code base, which is typical for large-scale projects, and especially if the code base is quite old, that is several years old. So you potentially have a lot of data. And the only way to make sense of the data when it's too much is to visualize it. Like, there's no other way. You can't use an Excel spreadsheet and look at the numbers to understand what happens. So that's good, because I'm kind of halfway through, maybe a little longer, but I have some time to show you some examples of code analysis that we can run, or that I can run. And by the way, you can develop, let me go back, you can develop these tools yourself anyway. There's no rocket science behind this. It's all very simple. So anyway, so the first type of code analysis that I'd like to show a few examples of are these, and I've run them through the code base of Redbubble that is a 10 years old Rails application. So you can imagine how much it may have evolved, and and how much technical debt it may have accumulated over the years. And so let's start with the hotspot detection. That is the first one. I need to find a way. All right. So I prepared these analyses before because it may take a few seconds, from a few seconds to several minutes to run these analyses, depending, again, on the size of the code base and on the period of time that you want to analyze. Let's see what we can have. Just have to do this. So the first one I want to show you is the hotspot analysis. That is an analysis that puts together the churn and the complexity of the code. And this is an enclosure diagram that we'll see many examples later as well, because it's very useful to describe the typical hierarchical structure of a file system where we have our code. And this is the entire code base of Rebubble, and you may not want to include the spec and all the test stuff in there if you want, but this is just an example. So what happens in here, we have obviously the size of these circles it's like proportional to whatever metric we are considering right now. So at this stage, I'm considering line of code, and this is all the way, the code is structured. And you can see that there's circles with a different degree of intensity of red. And those represent the modules, the files that change more frequently. And as a very basic principle, we know that if something is fairly complex and changes frequently, well, that may very well be something that we need to look at because it could represent a hotspot. So this is a quick way that helps us find, different hotspots. And when you dive in, you may, how much is that? So this is a bit to help us. This is the power of SVG. And you can see there are classes and modules in here that are the usual suspect anyway in a Rails application, like user. And you can see the user are like nearly 700 line of code. I'm ashamed to say this because I'm working on a bubble. And during that period of analysis that I took last year as an analysis period, 50 revisions. This is work, there is an entity that we have in Rebubble, and then we have, product, obviously. We also can filter by, churn level and start to, distinguish more interesting hotspot. We can also take a look at complexity analyzed in terms of cyclomatic complexity, which will give us a different perspective. And again, can pick up, for instance, these controllers, look at, application controller and shop controller. This is cyclomatic complexity. That's pretty high, like in the hundreds. So that's not very good. Personally, I think the lines of code is a better way to overall analyze because it's a language neutral way to analyze something that gives us a bit of an idea of how complex the file is. Obviously, it's nowhere near as accurate as other metrics that we can use, but at least it allows us to include everything that we have in our code base because everything has a number of line of codes. And in here, I can see that in our assets, we have some very interesting CSS files that are fairly big. And although we can't measure the complexity of the CSS file, well, I guess this is still not a good thing to work with. All right, so this is the first thing, hotspot analysis. Let's see other code analysis report that we can run. If we identify a particular piece of code, class, module, whatever, that has it's a very high complexity, we can look at the trend of this one. And we can see, okay, this is how the complexity changed from January last year to December last year. And you can see it started off with 263 and, well, ended at 341. And you can see that even though there's probably been some refactoring here that was made to mitigate this disaster, still, and you can zoom in and say, oh, what's happening here? And actually you can go in there and say, okay, I have a revision hash. I can go and see what happened there. Why did the complexity increase so much? But you can see, regardless of that there is a trend in here. There is an increasing trend, and this is worrying. So more than the peaks of this graph, I'm interested in whether, hey, is this file getting any better? No, it's not. So that's a problem. You also have other statistics that you can use around these metrics that give you an idea on how the complexity is distributed across the different methods of your classes. If you have a high standard deviation, for instance, it means that you have methods that are not complex, but then occasionally you have methods with high complexity. On the other hand, you have maybe a complexity that is distributed more normally against methods, but this is not really, the important thing is the other one. So another thing that is interesting to look at is the coupling. And by coupling, I mean logical coupling between between different files. And by that, I don't mean direct dependencies, like you may have direct dependencies, a class that uses another class or a module or something. What I mean by coupling is files that are indirectly coupled. And those are harder to spot. And those are typical of the problems that you have when you change a part of the code. You think you've done everything right, but then something else breaks that you didn't realize that was affected by your change. That's an example of coupling that is hidden in your code, and you can't see that coupling, like you can't see it by just reading your code. So there are a few analyses that we can run in here to kind of understand what the coupling is. The simple one would be this one, that if you have no idea where to start, gives you an idea of the most coupled files during that period of time. In order of number of coupling. And by number of coupling, in this case, we're talking about files that were committed at the same time. So that's the way that the CodeMat analyzes coupling. That is, if two files happen to be committed in the same time, then that's one hit. And the more hit you have with the same file, the more chance you have to be coupled to that file. And once we run this analysis, then we can, start maybe filtering through it and see what's in there. And if we're interested in a specific area, we can see, okay, the shop controller has a fairly high number of couplings, so let's see. And then we can run a temporal coupling analysis. The temporal coupling analysis gives us a description in time of how this file that we're looking at, and it's actually here, there is in blue my shop controller, how this file becomes coupled, well, and we need to be careful when we say that, in time with other files. By couple meaning there's a potential of coupling. For instance, we can look at this other period of time and start doing something like a movie. Then you can see in time how the different files are affected. And this gives us an idea of the effect that the change that we're making. Now, how do we identify whether a coupling is actually important or not? At that point, we need to start looking at the code, but when we identify the potential, the suspect, we have a good chance of finding something interesting. And another way is by looking at the degree of coupling that we have in everyone in here. So the coupling degree in this case is 19. So it means statistically there's a 20% of chance that if I change the shop controller, I have to change this file as well. So maybe 19 is not too much, or that I can't tell. But there's files with high degree of coupling in here. Like this one has 43, so 43%. What does have this finder factory, what does that have to do with the shop controller? That's like, and then I can start now looking at the code and see whether there is some form of hidden coupling, hidden dependencies in there that the developers didn't realize. And again, like all these analyses, I don't want you to think that they will give you the answer on what, how, then let's go and refactor. But I think they can really give you the first step into the investigation process. Like this is like we are police detective. We need to investigate. And we need tools that allows us to increase our learning and understand better our code base. Other type of analysis that we can do still on the technical side of things is, I call it system evolution. And by system evolution is tracking some metrics around our code base as a system, looked as a system. And in this case, what I've done is I partitioned the code base into areas that I call code, unit test, and end-to-end test. And I'm starting to look at some of these metrics and how they change in time with respect to each other. And for instance, let's look at the code churn, and let's remove end-to-end test because we're not writing any error bubble. And let's even just look at the other line of code and you see an interesting trend in here, that is the test code seems to follow the production code in terms of number of lines added after some time. They should go in sync, but they don't. And it means that, in this case, see, the code is adding, but the test actually is actually not following the trend. So it means that developers tend to write code first and write test later. Another interesting way to look at this is partition the system according to some other layers. For instance, I partition that into a typical, model view controller pattern that is in Rails. And here again, we can see that if I look at the code churn specifically, I can see that there's a huge, like we've been developing on the front-end side, like views is a logical name that couples all the code that goes into the front end. There's been a lot of development on the front end with respect to anything else. So that, again, this is all information that gives you a feel of how your team or your company, the entire developers in your company, how they work and how they, where are they putting their effort, and how does that affect everything else. Coupling is also an interesting one that shows you how are these different layers, again, coupled to each other. That is, how often when I change a controller, then also the views have to change. How often when I change a model, then maybe something else has to change. So again, this is just examples because there's no real recipes to run these analyses that are pre-made. You have to kind of explore your code base. Like I took, for instance, the date range as 1 year period, but that is really arbitrary. Like the period of time, you have to figure out what is the best period of time that you want to use, and you may have to have, to try different ones. And depending on how your software development lifecycle works, that is, if you release to production every 2-3 weeks, well, maybe you want to start running these analyses every 2-3 weeks and see what the changes are in time. That is everything as regard of the code, like technical analysis, and that's the last part is the most fun part, that is the social analysis. This is fun because it's something that has never really been done earlier. Like we always look at analysis tool as something that looks at the code and just tells us what's wrong with the code that is wrong with the machine. But let's look at the social aspect of the code because there is some in them. So let's look at some of these analyses. And the first one that I want to show you is the simplest one, and this is very easy. You could do it yourself without any of these tools anyway. And it's the commit message analysis, where I grab all the messages that come in the commit and I create a word cloud, obviously where the most frequent words are showed first. And even just looking at this, it tells you what's the language that your developers are using to develop and commit messages. Is it business language or is it more technical? And then you find out also what have we been doing in the first 6 months? Well, we've been adding a lot of stuff and at the same time fixing a lot of stuff, which is not unusual. Which is not unusual for a large code base with technical depth. You add because the business asks you to add, and then you fix because you break, right? Because this is pretty obvious. And remove, update, whatever. So this is the fun one to run. The other ones are actually even more interesting, I think. The other one I want to show you is the developer coupling. And this is, it kind of resembles the coupling between files, but tries to look at the coupling between developers. And this can be useful to find out whether you may have issues of communication between your team. And in here you have all your files that are, the bigger one are the one with the most developers touching it, and the redder one are the one with the most revisions. And then when you click on one of those and say, okay, who's touching this file? And okay, what other files are strongly coupled with this one? And then you can find out that this one is strongly coupled, and you can find out the main developer that is not the same main developer as this one. So you may start thinking, okay, are these two developers aware that they're working on the same file? Do they know? Yes, great, no problem. Do they don't? Well, let's make them talk to each other because they may end up stepping on each other's toes when they do the work. And, and you can do that for anything. So this is an interesting way it tells you, again, a coupling degree, that is the chance that can change and can affect changes. And the other one is the communication network. And don't be scared, this is the result of the monolithic Rails that I hate, but So this graph is basically, the concept is simple. It basically connects developers that worked on the same file during that period of time. And this graph uses an algorithm in D3 that is called force layout, which theoretically should group nodes, close a cluster of nodes together that have the most, the strongest link between them. So in an ideal world, you would like to see, in this case, the different teams in different colors to be cluster of nodes fairly isolated and separated. And they are not. And the other thing is, okay, I can start clicking on one of these and I can start seeing what all the links are with these developers. And okay, I can see that Erica is strongly coupled with, well, with Anthony, and, well, not really strongly, but this one maybe is more interesting. Oh, yeah, 4 shared commit. Oh, Miles, is Miles here? Oh, he's busy having a baby, I think. All right, so, but again, in here you can find out like these things and you know, and learn something. Learn whether there's dependencies between developers that you didn't know about that can cause problem, can cause, you know, your productivity to go down and everything else. Another interesting one is the developer effort. This is a way to understand how your teams put effort into every part of your system. And this is interesting because it gives you an idea on how fragmented the effort can be on different files. And if I go inside here and I start looking at my shop controller, and I can see that there's quite a number of developers that in last year worked on this, that's way too many. That's too many people trying to touch the same file. And that's not good, because you don't want this to be one developer only, because that would be considered a risk. You want to spread the knowledge, but at the same time, this means that there's a high chance that this file becomes corrupted and high technical debt very quickly. And you can, you know, you can see any other part of your system and see this thing not really being any good. But you can also find maybe good things. Let's see if I can find something. Like in search, I know we have a search team. See, there's a lot of green stuff in here. So this looks better. It doesn't seem to be so fragmented. But also you can look this by team. Again, this is where how the organizational structure can influence your effort. And the same thing you can look at from a team point of view and see how many teams are working on any component. Well, that's not bad, no, not bad, you know, 3 teams or something. You would like to see as few teams as possible. You would like teams to work independently, to work on part of the system that they own totally. And so in this case, you would like to see as fewer colors as possible in any file. Last is the knowledge map. And the knowledge map is a different way to look at the same thing. Like developer effort was based on number of revision committed by every developer. Knowledge map is based around number of line of codes added by every developer. So it's a slightly different perspective, but it also gives you an idea, again, where your knowledge, how your knowledge is distributed. And again, in here you have every developer is associated with a color. And you can see, for instance, that, what am I, hang on, up. You can see in here that in the assets, we have a developer owning lots of these files. And it's probably, if I remember correctly, Brad. Yeah, I can isolate him. And so what does this mean? Yeah, great, Brad is doing a lot of work, has done a lot of work last year, but if Brad quits the company, we have a huge hole in knowledge that goes out with him. So that's helpful to see, we better do something about that. And again, you can also have the team's view of that, which again should, in this case, on the contrary, should give you a better idea that is different areas should be as much as possible the same color, so you know that a team is working on that part of the code base and no one else. And that doesn't definitely happen in here. Yeah, okay. So, where are we? That's pretty much it. And I'd like to get, to at least for you, to have some of you interested in this, because this is very early days for these techniques. I haven't got any actual feedback on how effective these tools can be. So I've started to try and use this in Redbubble. I started to get other developers involved, but it's still early days. I don't have really much feedback. I don't know. I think there's potential in this, because I think that ultimately we need more data and better data to support our refactoring decision. We need to be able to go to the business with real metrics and show, hey, we're improving this. Otherwise, it will be a always difficult battle to convince, whoever pays us the salary that we need to spend 3 months refactoring a part of the system. We need to have data to understand, first of all, which part of the system is worth investing in and what metrics we're going to improve. I don't think there's time for question, but I'm here hanging out in here, so if you have any, yeah.
Yeah, mine is a CSI question. Yeah, when you show us the body parts, somebody else, I was thinking they're going to look at hacking and you want to perform a forensic analysis. So my question related to that is that how do you know somebody really hacking your system? Number two is that someone hacking to your routers and catching all your traffic. You really got all the information, you can use the software that you have to detect whether is it on the system or on the routers itself.
I would say probably not, but I mean, this information is all collected through version control. So if actually you have someone hacking your version control, you're in big trouble. I think, but like if someone really has the password to go into your version control code base, because I think most likely if someone maybe hacks into a production server and changes something there, but that you would never detect it through this, because this based all this information on version control, most of it, mostly. And the purpose is not yet to find real crime, offenders, but to find the part of the code that are the offenders in our code base. Yeah. Sorry, I didn't repeat the question. The question was whether we could use these techniques to find hackers, into the system.
If you were to start a greenfield project and you could measure, say, like just a few metrics to help keep that greenfield project, make sure that the code is nice and clean, what metrics would you be mostly looking at?
Look, I think it's a matter of trying. Like I've started to apply this because in Redbubble we have a problem with technical debt, and this is a way to, there's two ways to use this. One, to attack a already large-scale project and see if you can improve it. The other way, I think this could be perfectly usable in a greenfield project. I think you have to try which metrics you want to know, but I would definitely say the trend metrics are important, and the coupling metrics as well as the code grows, because initially it'll be pretty obvious what you see, but as the code grows and you start adding different subsystems and some modules, especially those inner couplings to me are really, really hard to find once the system grows to a certain size. And it'll maybe with this, and again, by iterating and running these analyses and comparing the results frequently, you can keep track of that. You can keep track of these metrics and say, hey, if there's something that has a coupling degree that goes over 30%, needs to be investigated and understand why. And as well, all the social metrics as well, to understand the couplings between developers. Those to me, the coupling it's the most dangerous thing that the technical debt introduces that is very hard to find, and you definitely can't find it with the traditional static analysis tools. Last question, if we have time, do we? No? No? Ask me later. Yeah, one more talk. That's like a quick.
Is there a easy way in the coupling thing where you couple individual files, you could put in a file path and reduce down to that? Can you do the opposite of that exclude?
Yeah, you can use a regular expression there, but that's just a functionality that can be changed. Like we could do that. That's just a simple diagram on a web page that uses some JavaScript to render, and I just did it. You know, that's also part of the feedback. If anyone starts using these things, I don't mind supporting these tools and actually even having people helping me out if they prove to be useful. Okay, thank you.